Hi, good morning, everyone. My name is Wenjia Wang, and today I'm presenting our research titled A Minimal Overlay-Based Framework for Transitioning Legacy Infrastructure to Zero Trust. And this work is motivated by a simple question. How can we bring zero trust to legacy system with a minimal cost? So here is a quick overview of my presentation. First, I will briefly contrast the traditional perimeter security model with zero trust, and why perimeter models are failing and why we need zero trust. Next, I will talk about the problem of adopting zero trust. Then, I'll introduce our proposed model and how we address the problem. So we will walk through the design of our model, how we implement our model on Azure, and then I will show you the results of our evaluation. So legacy infrastructure using perimeter model, which is shown in this figure, it's everywhere. Hospitals, universities, governments, and perimeter model divides the whole network into different zones to give different level of trust. But this model no longer works because remote work, bring your own device, and IoT. All of these blur trust boundaries and bring risks. For instance, in 2020, an attack to SolarWinds supply chain, a malware that hidden in a trusted channel was able to move laterally in 18,000 customer networks. And this attack cost a $90 million loss. And in 2021, a ransomware attacked Colonial Pipeline by using a single leaked VPN account, make the whole company offline for 6 days. And this caused a $4.4 million damage. And both attacks exploit implicit trust. The assumption that anything inside the firewall is safe. And that's why we need zero trust. Zero trust assumes that breaches have already happened. It enforces verification at every request. That's why zero trust is now being mandated by major regulators, including US management, Office of Management and Budget. They require zero trust architecture for all government agencies by next year. But the problem is, although we all know we need zero trust, but nobody knows how. Most literature in the area, they only treat zero trust as a concept, and there is no actionable implementation guidance. And perimeter-based infrastructure, they are very hard to change. They are very rigid. Besides, after decades of investment, it's too expensive to replace or rebuild from 0 to 1. So what did we do? Instead of replacing perimeter infrastructure, we proposed a minimal practical transition framework. So enterprises, practitioners, they can use our framework transitioning their legacy infrastructure to zero trust without major changes. So our model overlays zero trust capabilities on top of existing networks using just 3 open source components: identity and access management, public key infrastructure, and continuous diagnostics and mitigation. I'll refer to them as IAM/PKI and CDM in the following slides. Okay, now let's dig into details of what did we do, and why and how. So during our research, these two questions are central to guiding the development. Number one, what is the smallest set of components for a practical zero trust implementation? Number two, how can these components deliver immediate gains in brownfield deployments? So when we ask question number one, what are we asking? Smallest, practical. Smallest means using the fewest elements necessary to deliver essential zero trust functionalities. So first we have to define what makes a system truly zero trust. There is no such a so-called correct answer in the area. So we did a survey. Through a survey of major zero trust guidance and the literature, we found three principles repeatedly emphasized. Number one, identity verification, which means every user, device, and service must present verified and validate credentials. And number two, policy enforcement, which means least privilege access control. Number three, continuous monitoring. This principle means real-time visibility to detect threats and respond to breaches or policy changes. So we focused on just these three principles and selected only the components needed to achieve them. So this gives us a model that is good enough to be called zero trust while staying minimal in both complexity and cost. And our framework is also extensible. If an organization they want stronger security or additional zero trust principle in the future, they can just build up. So this figure is our model. We implement zero trust as a lightweight overlay on top of a legacy network. So compared to the perimeter model, there is no more zones. All the devices, no matter they are IoT devices or laptops, every device joins as a node using an identity within a unified overlay. So and the minimal stack we chose to satisfy the three principle we mentioned before is IAM, PKI, and CDM. And PKI is serving as a component of IAM. So as you can see, control plane and data plane, they are logically separate. So this split shrinks the attack surface. And of course, this split is a design from NIST SP 800 270. So the control plane is the brain of the operation. It runs on a dedicated like a control node and hosts our security service. It also includes a policy enforcement point or PEP server, which manages and distributes access policies. All other devices, like user endpoint or resource node, resource server, they all belong to the data plane. Each of these nodes is equipped with two lightweight agents. Endpoint, EA agent, which is endpoint access agent, and a PEP agent. EA agent handle initial enrollment and obtain the identity, and the PEP agent is used to enforce access policies. Okay, so how does a device actually join the overlay and start communicating? So this happens in two main phases. We have a diagram here for identity provisioning and kernel establishment. So for identity provisioning, we have four steps. Step one, we begin with an endpoint sends an enrollment request to IAM, and then IAM validates the request and ask PKI to issue a new X.50 certificate for the device. And then PKI generates the certificate and sends it back. So once the endpoint has its identity, it can establish or circuit over the tunnel. So for this tunnel established process, endpoint agent need to send the request to the server first. And then the server acting through the PEP server, after receive the request, it will check its policy and present its own certificate back to the endpoint. And then the endpoint will present its own certificate to the server for validation, and IAM will validate. And the last step, both sides, after both sides authenticated each other with their own identity, tunnel or encrypted tunnel will establish. And for zero trust, a key point is continuous monitoring. So establishing a tunnel is just the beginning. So this diagram, we were showing continuous monitoring and policy adjustment. So there are 4 steps. Step 1, periodic health data collection. And step 2, compliance reporting. Step 3, policy decision. And the last step, policy updates. This process is a constant feedback loop which allows system to adapt to changes in risk in real time. And next, we have implementation after we're done with design. So to validate our model, we built a prototype on Microsoft Azure using 3 virtual machines, and 1 for control node, 1 resource node, and 1 endpoint node. So the IAM and PKI service were built as using a lightweight Flask application, and we use strong Swan to establish the MTLS tunnels. And then EA agent and PEP agents on the endpoint, we implement those using shell scripts. And all the scripts and the process are in our GitHub report, by the way. So an important takeaway here is that our entire solution is built on open source software. So this means this process can be deployed with no new hardware, and no networking, rewiring, no licensing fee, no cost. Okay, next, evaluation. To test our framework, we built a simple file sharing application on these 3 nodes. So these 2 screenshots are the scenarios we activated and deactivated the tunnel. And as you can see, file transfer succeed when it's on and failed when the tunnel is off. So together, these 2 tests validate our security objectives, which is a syndicated entry and a least privilege. Next, performance and overhead. Security should not come at the cost of performance. So we have run uh, IPER F3 test, which is for it's a like a very common tool for network throughput. So the results was excellent. The overlay achieved an average throughput of 92.9, which is only 2.5% drop compared to the raw underlay. And um, the the resource overhead was also minimal. The entire control plane um, bundle idle only 8% CPU and like 320 MB of IM. And for endpoint agent, it consumed less than 1% CPU and only 30 MB of RAM. So these tests can confirm our solution is truly lightweight. And we have also conducted um, adversary test. So for our security objective number one, we confirmed a authenticated entry by attempting a replay attack with captured handshake pockets. So the system correctly identify them as invalid and rejected the connection. And for rapid containment, we tried revoke an active endpoint certificate, and the system detected the CDM detected it and detected the change and terminated the secure tunnel in just 8 minutes and 14 seconds. And our goal is under 10 minutes, so we achieved that. For objective 4, we tested for unauthorized lateral movement by creating a policy which is denied by endpoint node access to control node. So that connection was blocked and locked, which is a demonstration of the ability of this model to enforce least privilege. So in conclusion, we have introduced and validated a minimal, low overhead zero trust framework that can be deployed on top of legacy infrastructure without causing major disruptions. And our open source implementation provides a practical and accessible starting point for any organization looking to begin its zero trust journey. And here I have also listed our potential future directions. And here is the reference list. And that concludes my talk. Thanks for your time, and here is my email. Please feel free to reach out if you have any questions or ideas. By the way, I will also publish a full-length version of this work on archive in the future, which will have more technical details. And of course, this 6-page version, the copyright of this version belong to IEEE. And I will share the full-length paper link on this GitHub repo. Thank you again. Bye.